Welcome to the lecture module on optics. We are discussing wave optics and in particular the phenomena of diffraction. In the last lecture we saw diffraction by a single slit and a circular aperture. Today we will discuss the results of the circular aperture and how it determines the resolving power of optical instruments. So, the title of the talk today is resolving power of optical instruments, resolving power of optical instruments. So, let us quickly recall first the diffraction by a circular aperture which I discussed in the last lecture. So, here is a circular aperture, a beam of parallel light incident on a circular aperture. This is a block and there is an aperture here, a hole through which light passes. Because the aperture is small, there is diffraction taking place, and on a screen placed at a large distance we get what is called as the diffraction pattern, and for a circular aperture the pattern is called airy pattern, which is if you take a longitudinal cross section of this apparatus here, it would look like this, that parallel light incident here on the circular aperture, and on the screen we have an intensity distribution which is like this. So, this portion of the intensity distribution represents the central disk which is called the airy disk. Now, let me show the diagram more clearly, the airy pattern. So, the airy pattern here represents the intensity distribution due to Fraunhofer diffraction by a circular aperture is given by an expression of this form. As I mentioned in the last lecture, that the discussion of the derivation here is beyond the scope of our discussions here, and therefore, but the results are important for us, that is why we are giving you the result here and to discuss the implications of that. So, it is given by the intensity distribution is given by an expression of this form, where J1 is the Bessel function of the first order. V, the argument V here is pi by lambda into 2a sin theta, 2a is the diameter of the circular aperture, and the intensity distribution would look like this. We have discussed this in the last lecture, and we see that the intensity zeros are given by zeros of the Bessel function here, J1 of V, and it so happens that J1 of V is the first zero of the Bessel function occurs at V is equal to 3.832, and the second zero occurs at 7.016 and so on. Approximately 84% of the energy is contained within the airy disk. We have discussed this. Now, today we take it further and see what is the diameter of the airy disk, because in a laboratory setup we observe the diffraction pattern on the focal plane of a lens. The diameter of the airy disk on the focal plane, we want to estimate the diameter of the airy disk on the focal plane. That is why this is the screen is placed at a distance f from the lens, and here is the intensity distribution which we have. Now, we are seeing the intensity distribution along a diameter here along the x direction. So, if we rotate the screen like this, we would see a pattern like this with the intensity maxima here, with the intensity 0, and then again some intensity. The dot density here represents the strength of the intensity. The intensity is maximum in this part. So, the disk here, the airy disk here represents energy contained in this part. So, within the central maximum, that is the airy disk. The minima here corresponds to theta 1, the angle theta 1 shown in the diagram here corresponds to the minima on the screen, minima on the screen corresponds to the first minima, which is given by V1 is equal to pi by lambda 2a sin theta 1 is equal to 3.832. We have already discussed that this is the first zero of the Bessel function. This implies sin theta 1. So, we rearrange sin theta 1 is equal to 3.832, these go to the denominator 2 pi a into lambda, and 3.832 by pi approximately 3.14 gives us 1.22, and therefore, sin theta 1 is equal to 1.22 lambda divided by 2a, 2a is. Now, 1.22 lambda by 2a is much less than 1. We have already seen that lambda is of the less than 1 micrometer, whereas a is of the order of 1 millimeter or maybe 0.1 millimeter, and therefore, this quantity is much less than 1. In the earlier lecture, we have put numbers and seen that this quantity is of the order of 10 power minus 3, and therefore, sin theta 1 can be approximated by theta 1, because sin theta 1 is equal to this quantity, which is much less than 1, and therefore, sin theta 1 can be nearly approximated by theta 1 is equal to tan theta 1. And tan theta 1 in the diagram we see here w by this distance. So, tan theta 1 is w by this distance is f. Therefore, w by f is equal to 1.22 lambda by 2a. Theta 1 is equal to tan theta 1 is equal to w by f is equal to this, which gives 2w, the total spot size here, the diameter of this spot here is equal to 1.22 lambda f by a, where f is the focal length of the lens. Now, let us see this a bit more carefully and see what is the relation between the aperture size and the spot size. Now, if you look at the first diagram here, so this is the same diffraction pattern and there is the central maxima here. W is given by 1.22 lambda by 2a into f, because f is the focal length here, and when an aperture is of size 2a. Now, if we start opening the aperture, that is, if we increase the aperture size, please see the diameter of the lens here is d, aperture size is 2a, that is diameter of the aperture is 2a. Now, if we increase the diameter 2a, 2a is in the denominator, therefore, obviously, w will become smaller and smaller, this spot will start shrinking because w reduces, and therefore, this curve will start shrinking as the diameter increases. Now, if the diameter increases beyond d, what would happen? So, that is what is shown in the second diagram here. When the diameter of the aperture is more than d, parallel rays are incident, plane waves are incident here. Now, plane waves see the lens as an obstacle here, and therefore, diffraction takes place because lens acts as an obstacle here, but it also allows light to pass through and light gets focused after diffraction at the point here. Now, this is diffracted output because of the lens. It is a similar situation, except that 2a is now very wide and the input light is completely diffracted by the lens. So, you get a spot size here, again you get a spot size or an airy pattern here, but now R 0, the spot size, is determined by the diameter, not by 2a. In this case 2a, the case is 2a less than d. When 2a is less than d, w is given by this. When 2a is greater than d, that is when the aperture is large, then the lens diameter acts as an aperture and the diffracted spot size is determined by the lens diameter, and we get R 0, that is here the half width of the spot, just like w. So, R 0 is equal to 1.22 lambda by d, 2a is replaced by d into f, where f is the focal length of the lens. So, spot size versus aperture size. If you increase the aperture, the size of the aperture, then the spot will become narrower, spot will become smaller. Now, let us put some numbers and get a better feel for this. I have written here that the w is for typical numbers, w is of the order of 100 micron, but if you widen the aperture and if the lens diameter determines the spot size, then R 0 is of the order of 1 micrometer, because the lens diameter may be 5 centimeters, 2 centimeters, 5 centimeters and so on, while earlier in the aperture we had size of 1 millimeter, 0.1 millimeter, 0.5 millimeter and so on. Let us put some numbers to get a better appreciation of the formula. So, the typical numbers here. So, first I have shown diffraction by a circular aperture here. Typically, this is the wavelength I have assumed to be 500 nanometer, this in the visible region. Focal length of the lens is 20 centimeter. 2a, that is diameter of the aperture is 1 millimeter, gives us W is equal to 1.22 lambda by 2a into f. So, all are converted into meters, 500 nanometers, 20 here, 20 centimeters which is converted into meters, and 1 millimeter 1 into 10 power minus 3, which gives you 122 micrometer, or the size of the spot W is 0.122 millimeters, 122 micrometers. If we consider the second case, that is when the aperture size is greater than the diameter of the lens, then we get diffraction by the lens aperture. Lens acts as an aperture. Let the lens have a diameter of d is equal to 5 centimeter, rest of them parameters are the same. Then we have R 0 equal to 1.22 lambda by d into f. So, substitute as before. The difference is here 1 millimeter. Now, we have 5 centimeter, 5 into 10 power minus 2 meters. This gives you a spot size of 2.44 micrometers. So, the spot size here is much smaller compared to the spot size in the previous case, because of diffraction by the circular aperture. So, when diffraction takes place, as we have discussed in detail, light enters the geometrical shadow and light spreads into the geometrical shadow. Therefore, the size of the spot becomes larger. Now, therefore, from these discussions, let me see the conclusions. What are the conclusions that we have? The summary of the discussion so far. In diffraction by a circular aperture, the size of the airy disc or the spot size R 0 on the focal plane of the lens depends on the size of the aperture. We are repeating this, but this is summarizing it. Smaller the aperture size, larger is the spot size. When parallel rays, which can be represented by plane waves in wave optics, incident on a lens, they focus to a spot of finite size and not a point, as we saw in the case of geometrical optics. This would have focused to a point at the focus, but here it focuses to a spot of finite size, and the size of the focused spot is inversely proportional to the diameter of the lens. See here, size of the focused spot is inversely proportional to the diameter of the lens, which means larger the diameter of the lens, smaller will be the spot size. This has some implications which we will discuss in our next discussion. Now, we are ready to discuss the resolving power. The topic of the lecture is resolving power of optical instruments. Now, with these two conclusions, we are now ready to discuss the resolving power of optical instruments. So, let us quickly recall the optical instruments that we have discussed. So, we are to resolving power of optical instruments. In geometrical optics or ray optics, we have discussed 3 optical instruments. Recall that we discussed the telescope, microscope and human eye as an imaging device, Now, what we discussed earlier were details of image formation and magnification or magnifying power of these instruments. We discussed in detail, see lectures 8 and 9. In lectures 8 and 9, we have discussed in detail the formation of image and the magnification due to these optical instruments. Now, we are discussing resolving power of optical instrument. Why now? So, the question is why didn't we discuss this there? Because there we discussed in terms of geometric optics or in terms of rays, where the diffraction effects did not exist. The resolving power of optical instruments are primarily determined by the diffraction effects. Of course, assuming that there are no other defects, so the resolving power is determined by diffraction effects, and that is why we are discussing the resolving power of those instruments which we had studied earlier after knowing about diffraction. So, let us quickly recall. Let me show you the diagrams which I had showed. For example, this is a diagram which I had shown earlier, layout of the ray diagram for a telescope. There was a distant object and almost parallel rays come to this is the objective, that is the object lens, and this is the eyepiece. So, the simple telescope has two lenses, recall what we discussed earlier, objective and eyepiece. The role of the objective is to form the image of the distant object, and eyepiece helps us to see the image, a magnified view of this image. So, the image formation is determined by the objective, and the eyepiece helps us to see a magnified image of this as shown in this diagram. And then we have discussed about the angular magnification and so on. But now we are interested in this part only, the formation of the image and how diffraction effects affect the formation of image on the image plane. And similarly, we also discussed a compound microscope where we had an objective lens and an eyepiece. Again, the role of the objective lens is to form the image, and the role of the eyepiece is to see a magnified image so that we can see the image very clearly. What about the formation of the image itself? We discussed with one particular object here. Suppose there were two objects, where will be the images formed, and will we be able to resolve these images? That is the question which we are going to address now. So, telescope, microscope, and here I have a slide of the human eye also, which we have discussed again in detail. So, this is the human eye. Important point to note from the imaging point of view is the lens here, the imaging lens, eye lens, and the retina, that is the screen on which the image is formed. So, let us consider a telescope looking at a distant object. Let us take a specific example of a telescope looking at a distant object. Now, I have shown only the objective lens. As indicated, eyepiece, the eye lens helps us to see the image in a magnified form, but we are interested, we are concerned about formation of the image and the resolution of the image. And therefore, consider a distant object here, a source or a star which is far away. When L is very large, we can assume the rays coming or the light coming towards the objective can be assumed to comprise of parallel wave fronts, that is parallel rays or plane wave fronts. They can be represented by plane wave fronts when the object is at a very far distance. After passing through the lens focuses it to a spot, and we know that this spot is not a point now, it has a finite dimension. It forms an airy disk of diameter 2r0 on the focal plane. According to geometric optics, we would have got a spot here, we would have got a point here, whereas according to wave optics, we have a finite size and there is an intensity distribution on the image plane here. Now, if we have two sources which are separated by a distance here, S1 and S2 are two distant sources or objects which are imaged by the objective lens here on the focal plane. Then I have not shown the parallel rays, here I have shown the parallel rays and how the image is formed on the image plane here, but here I have not shown the parallel other rays, only I have shown this ray representing the central ray here passing through the midpoint of the lens here, and therefore, the image will be formed here, image of S1 will be formed here, image of S2 will be formed here, and there is an angular separation delta theta between the images which are formed. The intensity distribution of each image here, each image of these two sources, if they are sources S1 and S2, then the intensity distribution would look like this, which means the two peaks are clearly distinguishable, or on the image plane the images of the two distant objects are clearly distinguishable. Now, if I rotate this like this and see it more carefully, my objective is to determine what is the limit of resolution. Up to what separation between two sources we can distinguish them as two. The point will become clear if we see this image more carefully and come to the topic of limit of resolution. So, here it is. So, what is shown here is the same diagram. It is the same diagram which I have now rotated like this, and I am discussing only this region. So, the lower portion, because I want to determine when will these two images be resolved, when, up to what separation between the two, because the separation between the two will determine delta theta, and delta theta will determine the separation between the image on this plane. And therefore, we want to see how the separation here affects the separation here. So, here is the limit of resolution. First, when the objects are well separated, S1 and S2 are well separated, we see the corresponding diffraction patterns, namely the airy patterns here on the image plane, well separated, and the linear separation here is f times delta theta. F is the focal length of the lens, and f times delta theta will give us the linear separation between these two peaks. When the delta theta becomes smaller and smaller, the two images here start overlapping like this. This is the case that I have shown where S1 and S2 are coming closer here, which means the delta theta is reducing and the images start overlapping. According to Rayleigh criterion, the two images are said to be just resolved. They are just resolved when the maxima due to one image, the central maxima of one star or one image or one source coincides with the first minima due to the other one. And we know that the minima, the first minima occurs at an angular separation delta theta, which is equal to 1.22 lambda by d. We have seen the airy pattern in detail, and we have seen that the angular separation here from here to here, or let me take the diagram with the lens here. So, the angular separation theta between this and this is 1.22 lambda by d or lambda by 2a. So, the delta theta minimum corresponding to two objects or two sources, distant sources which are just resolved is given by delta theta minimum equal to 1.22 lambda by d. Delta theta minimum equal to 1.22 lambda by d is the minimum resolvable angular separation, and if we multiply that by f, so this is delta theta minimum, then this separation here between them S minimum equal to f into delta theta minimum will give us this. F into delta theta minimum will give the separation between the two images here, the peaks, separation between the two peaks is given by is the minimum linear separation on the focal plane of the objective lens, and 1 by S minimum is called as the resolving power. In optical imaging systems, the resolving power is the inverse of the smallest separation between two resolvable or two objects which are just resolved. If S minimum is the smallest separation between two objects which are just resolved, then 1 by S minimum is called the resolving power. Now, this is called the limit of resolution. So, let me discuss this more clearly here. So, and we come back again. Note, delta theta minimum equal to 1.22 lambda by d. I have written down it clearly here. The limit of resolution refers to the minimum angular separation delta theta minimum for which two objects are just resolved. Two objects are just resolved, that is, they are just distinguishable on the focal plane of the objective lens. According to Rayleigh criterion, two objects are said to be just resolved when the central diffraction maximum of one object coincides with the first diffraction minima of the other object. That is what I have shown here in this diagram here. The central maxima due to one object coincides with the first minima of the other object, first diffraction minima of the other object. So, this is Rayleigh criteria illustrated here on the image plane, and the corresponding delta theta minimum therefore is given by 1.22 lambda by d, because we know that this angular separation between the maxima and the minimum is 1.22 lambda by d. So, this is the meaning of this statement which is written here. The linear separation on the focal plane of the objective lens is given by S minimum is equal to f times delta theta minimum. So, here again this is the separation, linear separation. This was angular separation. This is the linear separation on the focal plane, which is f times delta theta minimum, and 1 by S minimum is called the resolving power of optical instrument or the resolving power of the device. The linear separation is given by this. So, I have repeated this and put it here, the summary of the discussions which we have had here. Now, this will become more clear when we take some examples. So, let us take one example and see whether we understand it or not. So, here consider two bright LED bulbs separated by a distance S dash. This is S dash, that is the distance far away. So, we have shown the diagram here. So, let me just show you the diagram here. So, S dash is the separation here and S is the separation here. When we discuss of the separation on the image plane, that is S, and that is why we had f times delta theta as S. S dash is the corresponding image, angle is the same, but the corresponding image at the distance L. The object may be at a far away distance L, and S is the separation between them here. So, S dash, if the observer, so bright LED bulbs separated by a distance S dash, that is the far away separation, glowing at a distance of 2 kilometer, this is L, L is equal to 2 kilometer from an observer. Consider two bright LED bulbs separated by a distance S dash glowing at a distance of 2 kilometer from an observer. If the observer is looking at them at night, I have written in the bracket at night because it is a bright bulb and at a 2 kilometer distance. So, if it is at night, you would be able to see that at night using a telescope of 5 centimeter diameter. Telescope of 5 centimeter diameter implies the diameter of the objective lens is 5 centimeter. So, telescope of some diameter means the diameter of the objective lens is 5 centimeter. What is the minimum separation for which the two bulbs are distinguishable? Assume that the wavelength of emission of LED is 500 nanometer. So, let us work this out, work out this simple example and then it will become more clear. So, we have two bright LED bulbs here with a separation between them. So, these are the bulbs and the separation between them is S dash. So, S dash is the separation between them. A person is observing these with a telescope of diameter 5 centimeter. So, 5 centimeter is the diameter. On the focal plane, this will form two images. So, here. So, this is the delta theta and this is f. Because this distance is very large, please see that this is L is given as 2 kilometer. If you are looking at moon or stars, then this will become hundreds of thousands of kilometers. So, L is a very large distance, f is small distance, typically f may be 20 centimeter or whatever. So, we have a 5 centimeter diameter is this. So, right now f is not given in this problem, only d is given, capital D is equal to 5 centimeter, L is given, S dash is this. So, the question is what is the minimum value of S dash for which, as we have discussed, we on the image plane we have. So, let me draw with a different diagram, different color. So, corresponding to this we have a spot with a diffraction pattern here, and corresponding to this we have another diffraction pattern, and the two bulbs are just resolvable if the maxima of this coincides with the first minima of this. That is, when delta theta minimum, if delta theta minimum, so delta theta minimum is equal to 1.22 lambda by d. So, lambda is given in our problem. So, wavelength is given, LED emission wavelength is 500 nanometer, d is 5 centimeter diameter, and therefore, this is equal to 1.22 into 500 nanometers 10 power minus 9 divided by 5 centimeter, 5 into 10 power minus 2, converting all into meters. So, this gives us 5 cancels and this is minus 7 and minus 2. So, minus 5, 1.22 into 10 power minus 5 radians. It is a ratio of two lengths. So, 1.22. So, this is the delta theta minimum. The question is what is the minimum. So, delta theta minimum on this side is the same as delta theta on this side, and therefore, the S dash here, S dash minimum, the minimum separation between the bulbs, so that it is just resolvable, is given by L times delta theta minimum. So, delta theta minimum. So, L is here given 2 kilometer. So, 2 into 10 to the power of 3 meters multiplied by delta theta 1.22 into 10 power minus 5 radians, now multiplied by meters. So, this will be so many meters, which is equal to 2.44 into 10 power minus 2 meters, which is 2.44 centimeters. If the two bulbs are separated by 2.4 centimeters, while viewing through the telescope, the bulbs are, the images are just resolved on the focal plane here. That is the meaning of this. Therefore, the minimum separation, please see whether we have answered the question or not. So, what is the minimum separation for which the two bulbs are distinguishable? Separation here is given, separate, the bulbs are separated by a distance S dash here. So, this the minimum value of S dash which has been asked. In some problems we may be asked the separation S between the images formed on the focal plane, but here the separation between the bulbs, which means separation between the two objects which have been asked, which is denoted as S dash. So, S dash is equal to L into delta theta minimum, whereas S, the separation on the focal plane, will be equal to F into delta theta minimum. Okay. So, let us take one more example. Oh, before we take one more example, let us look at the second problem, that is limit of resolution of human eye. It is closely related. So, we have seen the limit of resolution of a telescope of diameter d, which means the objective lens of diameter d, and the minimum resolvable angular separation is delta theta minimum given by 1.22 lambda by d. Now, let us see the limit of resolution of human eye. Now, so I have illustrated here in this diagram. So, here is the human eye. So, I have not given more details, but we are interested in the lens here. And what is the aperture? In front of the lens we have iris, that is variable diaphragm. This is a diaphragm of variable aperture size, and that aperture is called pupil. So, here is the pupil. So, pupil is shown here. So, this is the pupil. The diameter of the pupil varies, usually this varies from about 2 to 8 millimeter in human beings, depending on the amount of light present. So, this is the pupil which is of diameter d, the lens is here. So, the pupil acts like an aperture which is placed in front of the lens. So, the objects, the two objects S1 and S2, or two sources S1 and S2 separated by a distance S dash forms images here on the retina. Retina is placed at the focal plane of the lens, and therefore, the images are formed on the retina. As we know, these are not points, but they have a finite intensity distribution which is given by the Airy pattern. So, the linear separation here S is given by f into delta theta minimum, delta theta here. So, delta theta is the same as delta theta here, f into delta theta gives us the separation on the retina, L into delta theta gives us the separation S dash. So, please see here, delta theta minimum is equal to 1.22 lambda by d, the minimum angular separation for two objects to be just resolved, and S minimum here will be f times delta minimum. S dash is equal to L times delta theta, that is the linear separation at a large distance L, and S dash minimum will be equal to L times delta theta minimum. So, d is the diameter of the pupil. Typically, as I mentioned, the diameter varies from 2 to 8 mm in human beings. Now, let us take an example to understand this limit of resolution of human eye. So, example 2. Here I have taken the same problem, same example, except that now we are not observing with the telescope, but observing with the human eye. So, consider two bright LED bulbs separated by a distance S dash glowing at a distance of 2 kilometer from an observer. This sentence is the same as that sentence. So, it is the same sentence, first sentence is the same. But in here in the second sentence, the observer is looking at them using a telescope, but now here the observer is not looking at them using a telescope. What is the minimum separation between the bulbs for which the observer will be able to distinguish them? Assume that the diameter of the pupil of the observer's eye is 5 millimeter and wavelength of emission of LED is 500 nanometer. The example is simple, we have already worked out this example, and let us work it out again here. So, we have the same two LED bulbs now. So, here I have represented with a separation S dash. So, what would be S dash if now you are the observer is just looking at it. So, this is his eye with the so this is the optic nerve, and here is the pupil. So, that is the pupil. So, the pupil is here. this is the pupil. Given that the pupil is 5 mm, pupil diameter is equal to 5 mm dia. This is given. The distance is given, distance from here to here 2 kilometer. The same distance, in the first example he used a telescope, now he is not using a telescope, and therefore, the images are formed here. So, one image, the second image. So, what is the delta theta minimum? Delta theta minimum, we have to find out delta theta minimum to get S dash minimum. So, delta theta minimum is equal to 1.22 lambda divided by d. Now, d is the diameter of the pupil now, this diameter of the pupil. So, d is given as 5 mm, lambda is given as, so this is 1.22 into 500 nanometers, 500 into 10 power minus 9 divided by d is 5 millimeter. So, 5 into 10 power minus 3. So, minus 6 and minus 2. So, minus 4, 5 cancel. So, we have this equal to 1.22 into 10 power minus 4 radians. In the earlier example, we got 1.22 into 10 power minus 5 radians, because we were looking at a lens of diameter 5 centimeter. Now, the pupil which acts as the aperture here is only 5 millimeter wide. So, that is why this delta theta minimum has increased to by an order, that is by a factor of 10, and therefore, S minimum, S dash minimum, S dash min is equal to L, that is L into delta theta min, which is equal to 2 kilometer, 2 into 10 power 3 meters into 1.22 into 10 power minus 4 radians, which is equal to 2.44 into 10 power minus 1 meter, which is 24.4 centimeters. Now, it is 10 times more, just because the diameter of the pupil became smaller by 10, therefore, this became 10 times larger. The minimum separation, that is, if the bulbs are separated by a distance of 24.4 centimeters, earlier we got 2.44 centimeter, that is with the help of a telescope, but when he looks at the two bulbs with his naked eye, then the bulbs had to be separated by 24.4 centimeters if the two have to be distinguished. So, this indicates the importance of diffraction effects in resolving objects at a large distance. That is why the name resolving power. Let us now look at the resolving power of the optical microscope. Resolving power of a microscope refers to the ability of a microscope to resolve or distinguish the smallest possible features of an object. It refers to the ability of a microscope to resolve or distinguish the smallest possible features of an object. What do we mean by this smallest feature of an object? For example, let me show you what it means. If you have a subject, so smallest features, what do we mean by this smallest features? Smallest features. For example, if you have a sample whose surface has corrugations on the surface, corrugations, let us say variations like this. The surface is not very even, it looks even, but if you see under a microscope, then you may see surface corrugations like this. So, this is a sample, so it is a sample with surface corrugations. The smallest features here refer to this separation here. For example, if the microscope can identify this peak as well as this peak, it means
it can distinguish between the two peaks, and we say that the separation between them is the smallest feature. The smallest feature refers to the smallest separation, in this case for example, that the microscope can distinguish. Similarly, if you take for example blood sample, we know that the blood sample is taken on a microscope slide and then it is observed under a microscope. There may be blood cells, so these are the blood cells. Whether the microscope can identify these separately or not, what is the smallest separation it can measure between this? For example, if there are large number of cells almost overlapping, then can the microscope distinguish these? Of course, you can always dilute the sample, but whether the microscope can distinguish these or not. For example, if you have a material or a surface where there are stripes like this, a material which has stripes, we are talking of very small dimensions. For example, this separation may be of the order of 1 micron. This separation may be 1 micrometer. Can the microscope identify these separations? So the smallest features which a microscope can identify, that tells us the resolution or the limit of resolution of the microscope. So we come back to the definition again. Therefore, the resolving power here refers to the ability of the microscope to resolve or distinguish the smallest possible features of an object. If S minimum, here S minimum is the minimum separation that can be measured between two just resolved features, as I showed you, for example, those corrugations, just resolved features of an object or sample, then S min, that is the separation, is called the limit of resolution, and 1 by S min is called the resolving power of the microscope. So let's see further resolving power of the microscope. Let's recall the microscope itself. So let us see the microscope, the scope which we had seen in lecture 9. So I am putting that diagram again here. So there is a small object here which is placed just beyond the focal length of this objective lens. This is the objective lens of a compound microscope, and there is an eyepiece. The object is placed just very close to the focal length of the objective, and the image is formed here. So this is the image plane where the image is formed. Of course, the role of eyepiece is to see a magnified view of the image, but the formation of the image is determined by the objective lens. Once the objective is able to resolve small features, the eyepiece will help us to see it with a magnified view. Now let me see what we are. If we take the lens here and we saw that we started with a small object like this, and then we got, I will show only the central ray, then we found an image here on the image plane, an enlarged image here, inverted but enlarged image here. So this is just beyond the focal length f. If I had another object, like this, an arrow, inverted arrow, then I would have formed, it would have formed an image here. So this is the image of this arrow. If we look at points, for example, if we look at the tip of this and the tip of this and the midpoint here, then we would get an image of this form. So let me show you. We are looking at the point only. So there is one point here and one point here. Let me see the points. So P1 and P2. So this would form an image here, and this would form an image on the axis. Let me consider 2 points of this object here, 2 ends of this object. If this is a point object and there is a point object on the axis, it will form corresponding image on the image plane. So, it's the same plane as this. Now, we know in wave optics, in ray optics, if there is a separation here, there will always be a separation here. But in wave optics, even a point object forms an airy pattern here on the image plane. So, we will see an airy pattern corresponding to the 2 point objects. Now, the image will be resolved or not is determined by how much overlap these images have on the image plane. As we know from the Rayleigh criteria, that if the first maxima of one image coincides with the first minima of the second image, like this, we have discussed this in detail, I am just repeating it, that then we say that the two objects are resolved, and this separation delta theta min, the minimum angular separation when two objects are resolved, is given by delta theta min is equal to 1.22 lambda by d, where d is the diameter of this lens. And the corresponding separation here is called S min, is designated the minimum separation which is resolvable, and this is the S min. And therefore, let me show the diagram more carefully now. The limit of resolution of a microscope, therefore, the limit of resolution of a microscope is illustrated here. So, let us see the same diagram. I have drawn a pre-drawn diagram. The 2 point objects are here, P and Q. I have shown the ray like picture here, but these are waves now, waves coming out of these two. Let us say these P and Q are point sources. They reach here on the image plane, and there are airy patterns formed here, and intensity distribution is shown here. The delta theta minimum is given by 1.22 lambda by d. Sin delta theta min is equal to 1.22 lambda by d for P and Q to be just resolved. The separation then is identified as the minimum resolvable separation. Since lambda by d is much less than 1, we have put some numbers. For example, this diameter may be about 1 centimeter, and lambda, as you know, is less than 1 micrometer, which means this ratio is of the order of 10 power minus 4, which is much less than 1, and therefore, sin delta theta min can be equated to delta theta min, and therefore, S min is equal to, that is the separation here, there is a very small angle, and this separation, the object is very close to the focal length of the objective, and therefore, we can write S min, that is the smallest resolvable separation, is equal to FO, this is FO, focal length of the objective, which is very nearly equal to the image distance u, FO into delta theta min. In fact, the objects to be viewed under a microscope are placed on the focal plane of the lens, very close to the focal plane of the lens, and therefore, this is equal to 1.22 lambda by d into FO, where FO is the focal length of the objective. Let us discuss this a little bit more. Note that S min is 1.22 lambda by d into FO. The expression for S min looks identical to that obtained for the telescope. We remember that this is the same expression that we got in the with S min, but there S min was the smallest separation on the image plane. Now, this S min is on the object plane, point number 1, and it looks almost, otherwise the expression looks similar. In the case of a telescope, the emphasis was on increasing d, the diameter of the lens. That is how we discussed about 2-inch telescope, 5 centimeter telescope, 10-inch telescope, and so on, where the number was referring to the diameter of the telescope lens. In the case of a microscope, one chooses an objective of shorter focal length. If you reduce the focal length, S min will reduce. A very good resolving power refers to a very small value of S min, and therefore S min can be reduced by either reducing the wavelength or reducing FO, and of course or increasing D. In mathematics it looks that D could also be increased. That is what we did in the case of a telescope, but in the case of a microscope this is not what is done, but FO is reduced. That is, objective of smaller focal length is chosen if we want to get a larger resolving power or smaller value of S min. Why? There is a question here, why? And the second, of course, is the choice of a shorter wavelength to observe the object would also improve the resolution. Smaller value of lambda means smaller value of S min. Typically, FO, these objectives, objective focal length of the objective is of the order of a few millimeter here, and maybe a few centimeter, few millimeter to few centimeter, and D, the diameter of the objective lens is about a few mm. So I can show you, I have a objective here, you can probably see the objective. So let me keep on the plain paper. So there is an objective placed here. So this is the diameter of the objective lens. This I suppose you may have seen these. These are microscope objectives which are fitted at the bottom of the microscope tube, and you normally have several microscope objectives fitted under the to the microscope tube, and you can change the magnification by choosing appropriate microscope objectives. So I have just picked up one of those objectives, and as you can see that the diameter here is a few millimeter, the diameter of the objective lens. So let me take quickly an example here, and it should become more clear with an example. So a particular object which is to be observed under a microscope has a periodically corrugated surface of period 1 micrometer. The objective lens of the microscope has a diameter of 5 millimeter and focal length 10 millimeter. If the object is observed with the light of wavelength 600 nanometer, will the corrugations be seen clearly? The answer to be given is yes or no. Justify your answer. Let me repeat again. A particular object which is to be observed under a microscope has a periodically corrugated surface. As I showed you, a corrugated surface with the period 1 micrometer. So you have to resolve separations of 1 micrometer. The objective lens of the microscope has a diameter 5 mm, which means D is 5 mm, focal length 10 mm, and the wavelength of observation is 600 nanometer. Will the corrugations be seen clearly or not? Let us work this out. So we have here delta theta min is equal to 1.22 lambda by D, and therefore S min, what is the S min which is permissible for this microscope, which is FO into delta theta min, which is equal to FO, the focal length is given 10 millimeter. So 10 into 10 to the power of minus 3 meters multiplied by delta 1.22 divided by D, diameter is given 5 millimeter. So 5 into 10 power minus 3 into wavelength lambda. So let us see, this is straight away, this cancels, this is 2. So we have 2 into 1.22 lambda, 2 into 1.22 into lambda. Lambda is given as 600 nanometer. Wavelength of light is given 600 nanometer. So 600 into 10 power minus 9 meters. So, we can see that this is 6 into 2 is, so this is 12. So, these we can remove and write this as 12 into 1.22 into 10 to the power of minus 7 meters, which is equal to, so 12 into 2 is 24, 12 into 2 is 24 plus 2 26, 12 into 1 is 12 plus 2. So, 1464. So, this is 1464 into 10 power minus 6, because it was 12 into 1 point something, we were getting 14 point something. So, I have written 1.464 into 10 power minus 6 meters, which is equal to 1.464 micrometer. This is the minimum which is resolvable by the microscope. However, the question says the object has a surface with a periodic corrugation. It's periodic. Periodic means all the corrugations. I have shown triangular corrugations. It need not be triangular. It could be a different type of corrugation. So, this period here, this separation is given. The separation is given as 1 micrometer. Periodic means all of them will have the same separation, which is 1 micrometer. We have got that S min is equal to 1.464 micrometer, and therefore 1 micrometer cannot be resolved. So, the answer is no, the corrugation cannot be resolved, cannot be resolved. Please see, if we had a lens, if we had an objective of focal length 4 mm here, instead of 10 mm, if we had 4 mm, then we would have got, instead of 10, we would have got here 4 instead of 10, and then the factor would have been reduced. This would have been reduced by a factor of 2.5. So, because this is 10, if I replace it by 4, the answer will be 1.464 divided by 2.5. So, 2.5. This will be less than 1 micrometer, which means S min, the smallest observable separation, is less than 1 micrometer, and in this case we would have been able to observe the corrugations. So, you had a microscope objective with a 10 mm, but if there was an objective of 4 mm which was smaller, then we would have been able to resolve this. So, that this clearly shows the importance of choosing smaller focal length objectives to achieve a better resolution. Now, there are number of possible exercises which one can work out to get a better feel for the effect of diffraction on limiting the resolution of optical instruments. So, more number of examples would make it more clear, and diffraction has this inevitable effect on determining the resolution of optical instruments. Thank you.